Okay guys, lastly, lesson 6, why do chemical and physical changes occur? This is going to bring in entropy and enthalpy for the final part of this unit. Alright, so turn your pages to page 17 and we will begin. So entropy, or delta S, unlike enthalpy, which is delta H, it is the degree of randomness or chaos or disorder or messiness in a system. Nature tends to proceed to a state of greater entropy or disorder. Gases would have the highest entropy because they are least ordered. Okay, think about particles all over the place. Okay, and they're colliding and they're going all over the place. Okay, so it's very messy. So the more order you have, the less entropy in your system. The less order you have, the more entropy in your system. So going from solid to liquid to a gas, what is the most significant factor in determining delta S? Changing from solid to liquid to aqueous to a gas phase, you will experience increased entropy. So what I would like you to do, or actually we'll do it together, draw particle diagrams to illustrate each of the following phases. So a solid, you would have a nice, compact, ordered system here, okay? Virtually no entropy. Okay, a liquid then becomes a little more random. Particles all over the place, on top of one another. Okay, that would be a liquid. Then aqueous phase we have, okay, same structure as the liquid, but we'd also have other particles in there. Remember, you have things all over the place, evenly dissolved in that liquid. So I'm just coloring some of these circles to indicate particles on top of particles, okay? And then finally a gas, where particles would be all over the place, and I'm just indicating their direction of travel, okay? So entropy increases when a compound is broken down. This is very important. So when you look at a reaction, you need to figure out if there's one reactant and two products. Okay, broken down. And then entropy decreases when a compound is created and bonds are formed. Less messiness, less chaos, less disorder. So here's the rule. If there's no phase change, what you're going to do is you're going to count up the number of molecules on each side. The rule is that if the number of moles goes down, entropy goes down. And that would give you a negative delta S. If the number of moles on each side goes up from left to right, then the entropy is going to increase. So less moles, less to more, would mean a greater entropy. Okay, so less to more would be an increase in entropy from left to right, and then more, and then here's the arrow, to less moles would be a decrease in entropy. Less things to make messy, right? All right, so what we're going to do is we're going to practice looking at some equations here to determine if there's an increase or decrease or no change in entropy. So for number 1, you have 2KClO3, okay, so there's one reactant, and now I have two products. And I have a solid and a gas, which means that I have more moles, right? I have 2 moles over here and 5 over here. So the rule is if I go from less to more, that this is going to increase. Okay, more chaos, more particles going all over the place. Okay, it's a mess. Number 2, I have a liquid to a solid, all right? And going back to the rule, remember, from solid to liquid to aqueous to gaseous is increasing your disorder. But we're going from a liquid to a solid, so particles are actually becoming more arranged. So there's a decrease, okay, in entropy here. Now, for number 3, we have a gas and a gas forming a new gas. Now this is when bonds are created. So entropy is actually going to decrease because a bond is formed and we have less moles on this side, okay? We have 2 here and then we have 4 over here because we're going to think there's 1 there and 3 here. So there's a total of 4 on this side, 2 on this side. So more to less is a decrease in entropy. Now we have a solid going to an aqueous phase, and this is where a bond is broken, so this is going to increase entropy. Lots of disorder there. solid to a liquid. Again, the rule is solid to liquid to aqueous to gas, increase in entropy. All right, number 6, we have a solid to a gas directly. So does anybody remember what that's called? Well, we have an increase in entropy, and then I'd like you to tell me what this phase change is called. For number 6, what is that called? And be ready to answer that in class. All right, number 7, we have an ion of hydrogen and an ion of acetate, and they form a new product, okay? So this is actually decreasing entropy here because a bond is being created. Now here we have a solid and a gas to all gas, bond is being formed, so there's a decrease in entropy. What I'd like you to do is try the rest on your own using these rules, okay? So go back to your notes, look at the phases. If it's all gas, then you need to count the moles, okay? If they're all the same phase, either way, gases or all aqueous. And then also check to see how it's going as far as phase change, okay? Remember, the rule is it goes from solid to liquid to aqueous to gaseous in that order for increasing entropy. All right, and finally, enthalpy. Now, we'll go over the previous examples in class. I want to check to see if you understand entropy. So enthalpy is delta H. We've already discussed this in a previous unit. It's the energy in a system. Okay, nature tends to proceed to a state of lower enthalpy or lower energy. All right, exothermic reactions release energy and move to a lower energy state. Most common types of reactions because less energy has to be put in to get the reaction started. So there's a lower activation energy for exothermic reactions. These are favored, okay? So exothermic reactions are favored in nature. Because less energy is needed. Okay, you don't really want to input a lot of energy. And then finally, endothermic reactions absorb energy and move to a higher energy state. Higher activation energy is needed, so not as common because more energy must be put in to get the reaction started, which means a higher activation energy again. Okay, very important. So notice, all right, lots of activation energy here, where the other diagram is like this. Okay, less activation energy. So this is exo here. Okay, and notice the difference in products and reactants and the energy of each. All right, so actually that finalizes Unit 8. Thank you guys for listening to my video lessons, and hopefully we can get some review done.